Today we're looking at a problem that is popular among professors that seek to instill a general understanding of the physics principles among their students. The question is, for a light damped oscillator being driven near resonance in the steady state, show that the fraction of its energy that is lost per cycle can be approximated by a constant, which we'll determine divided by a factor of Q. Now, we know the total energy of a harmonic oscillator is the sum of its kinetic and potential energy. For a simple harmonic oscillator with mass m, natural frequency omega naught, and amplitude a, equation 1 is how its energy total can be represented. This is the sum of both its kinetic and potential. Now, if this doesn't make sense to you, let's go ahead and derive this real quick. Now remember that the total energy of the system is based off both the kinetic, the K, and the U, the potential, which for a simple harmonic oscillator can be visualized as 1/2 mv squared plus 1/2 kx squared, where v is the velocity, m is the mass, x is the displacement from equilibrium, and k, more commonly known as a spring constant, we can think of it as the potential constant, because this scenario works for springs and really any simple harmonic oscillator. Also, a good thing to note is that k is being the spring constant can also be written as m times the national frequency squared. Remember, we can represent the x position as a sinusoidal. If you look at 1.2, we can represent it as a times cosine times omega t plus some type of phase shift. Now, it turns out this phase shift won't, I included to be proper. We won't really need it in our problem, as you'll see shortly. V, that's the velocity. That's simply the derivative of the x, and that gives you 1.3 minus a omega naught times sine. If we plug in equations 1.2 and 1.3 into 1.1, we get this long mess of an equation, as you can see right here. Going to right below it, you can see that the equation is, we can plug in k is equal to m omega naught squared. Since we are driving this at the frequency omega is approximately equal to omega naught, we can factor terms. We can factor out all the multiples, leaving us with these terms out in front and these sinusoidal here in the middle. Now you should notice from the middle, if you remember your trigonometry, sine of t squared plus cosine of t squared, or sine squared of t plus cosine squared of t is equal to 1. This gives us this equation. Now, we know where equation 1 comes from, so let's proceed with the rest of the question. The quality factor for any simple harmonic oscillator is omega naught times the energy stored per cycle divided by the energy lost per cycle. This can also be defined as omega naught over 2 gamma. This is the definition of a damped oscillator, and we'll go into this a little bit further. For now though, don't worry about gamma. We know that the energy lost per cycle is related to the damping force, which is proportional to the velocity. If we assume B to be the damping constant, the power dissipated by the force, aka the rate of energy loss, is P dissipated is equal to force damping times V is equal to minus BV squared. From this, we can get a total energy loss from one cycle by integrating it over one period. We'll call this total energy loss delta E, and the period being from 0 to 2 pi over omega naught. Here, delta E is equal to the integral of power with respect to time from 0 to 2 pi omega naught. Plug in what power was, minus BV squared. Plug in V for that. And we're left with this little equation. We know this, we can do calculus to go further if we wish, but we're going to go ahead and make it a little easier on ourselves. We know that sine squared can be transformed using a trigonometric relation using the half angle formula. 1 minus cosine over 2 omega naught times t plus 2 times the phase shift, all over 2. If you look on the screen, you can see this graph of of cosine. While it's not completely accurate, it's just a hand-drawn mess, it leaves us with the same amount area above as below. So we know this thing is going to contribute nothing to the integral due to symmetry. Integrating that turns out just to be pi over 2 omega naught, giving us the final answer of delta E, the total energy loss, being this relation, minus BA squared times omega naught times pi all over 2. And then, if we want to find the total fractional of energy loss per cycle, we just need to take equation 4 and divide it by equation 1. Giving us number 5, B times pi over m times omega naught. Now we're almost done. Once we can convert equation 5 in terms of Q, we'll be completely done. Now remember, the gamma term is actually called the damping coefficient, and it's actually very closely related to the damping constant B. If the oscillator has motion based on the equation where m times the acceleration plus b times the velocity plus k times x is equal to 0, we can rewrite this whole thing by dividing the entire equation by m and setting gamma equal to b over 2m. Plugging this equation 2 gives us our explicit equation for factor, which is just q is equal to m omega naught over b, giving us equation 6. We can plug this equation 6 into equation 5 and get our final answer, where the total energy loss per cycle, a fractional energy loss per cycle, is pi over q. It turns out the mystery constant was pi, as it often is, and the higher the quality factor, the less loss per cycle.